Hi, and welcome to this video on the modulus of a complex number. So what's the modulus of a complex number? Well, to understand this, we need to think about how we plot complex numbers. If I start with a complex number a plus b times I, we know that when we write this, we mean that a and b are actually real numbers, and I is the square root of -1. And so we've learned that we can plot these things in the complex number plane by putting the a, the real part, on the real axis, and b, the imaginary part, on the imaginary axis, and plotting it almost like a point in R2. Let's look at an example of this, and then we're going to get into the main concept. Look at the example 5 plus 4 times I, and let's plot that point in the complex number plane. I would need to go out to 5 on the real axis, because that's the real part of the complex number, and up 4 on the imaginary axis. So I would go to this point right there. I'll just put an X there and kind of fill it in, and that right there would be my point 5 plus 4i if you graphed it. Now, the modulus of the complex number comes from this question here. How far away from the origin is that point that I just drew? So how far away is it? Well, if I connected that point back to the origin with a line segment, I would just want to calculate the length of that line segment. So how long is that? Well, to find the length of that line segment, I can just use the Pythagorean Theorem. If I imagine a perpendicular being dropped right down to here, I see I've got a right triangle with 5 on this leg and 4 on this leg. So the length of this line segment here would be the square root of 5 squared plus 4 squared. And so just to finish this off, that would be the square root of 25 plus 16. That's the square root of 41. That's how far away from the origin that complex number is if I plot it. And that length is what we refer to as the modulus. So we're going to make our definition here. The modulus of the complex number a plus bi is, we're going to use a notation involving absolute values. We're going to write this symbol right here, and it's going to be defined to be the square root of a squared plus b squared. This is really the Pythagorean theorem. I'm taking the square of the real part, the square of the imaginary part, adding the squares together, and then taking a square root. And what that calculates is the distance of that complex number from the origin. It's the complex number analog of the same thing we do when we take the absolute value of a real number. When we take the absolute value of a real number, we're really just calculating how far from 0 is it. And we're doing the exact same thing here. It's just that the geometry is a little more sophisticated. So let's do some examples up here in the corner. So first of all, what is the modulus of 3 plus 2i? Well, by definition, this would be the square root of 3 squared plus 2 squared. That's the square root of 9 plus 4, which is the square root of 13. That tells me again that this number 3 plus 2i is square root of 13 units away from the origin. What if I took the modulus of 4 plus 0i? Well, that would be the square root of 4 squared plus 0 squared, and that would just be 4. And that makes sense because the complex number 4 plus 0i, if I plotted it over here in the plane, would go right there. It's along the real axis, and so it's obviously 4 units from the origin, and the math bears that out. I would get the same thing if I had taken the modulus of -4 plus 0i. That is also going to be equal to plus 4. And one last example, what is the modulus of 3i? Well, intuitively, what I should expect is 3i is plotted right there, so it ought to be 3 units from the origin. If I apply the definition, I believe that is what we'll get. That is the square root of 0 plus 3 squared, which is indeed equal to 3. So that's the modulus of a complex number. We have a formula for it right here that's fairly simple to understand, and what it tells you is geometrically it gives you the distance of the complex number from the origin.